Ever stop to think about what's really going on? Like deep down, when you run almost any software,
Yeah.
your phone apps, cloud services, even games. There's this invisible engine kind of humming away behind the scenes, takes the code we write, the human-readable stuff, and turns it into the super fast instructions the computer actually gets. And understanding that engine for programmers, it's not just interesting, it's like a real advantage. Gives you insight into performance, control. It's pretty fundamental. So today we're doing a deep dive into that engine. It's called LLVM. And yeah, LLVM, it's not really an acronym anymore. That's just its name now. Our mission here is to unpack it, make it less intimidating, and show you just how much it impacts software development. We got a research report on LLVM internals guiding us, so expect some cool insights.
Exactly. And, LLVM might sound super technical, and parts of it are, but the core ideas, they're really about making powerful tools simpler and more flexible, which is why it's actually really important for anyone programming to kind of get a handle on it. We're hoping you'll have some of those aha moments today, really see how modern compilers work and why LLVM was such a big shift.
Okay, so to really get why LLVM is a big deal, maybe we should quickly look back. What was the scene like before LLVM? You hear about these like monolithic compilers.
Yeah, monolithic is a good word for it. Before LLVM, compilers were often these huge single pieces of software. Everything was tightly woven together, making changes like adding support for a new chip feature or trying a new optimization. It was tricky, really difficult. Like surgery without a map. You could tweak one thing and, well, break something else entirely unexpected. Very rigid, hard to extend, definitely needed something more modular.
Right, and that's where LLVM steps in, right? Came out of the University of Illinois around, 2002? What was the big idea then?
The really ambitious goal right from the start was this modern approach using something called static single assignment, or SSA. We'll get into that. But instead of another monolith, they envisioned LLVM as a compiler infrastructure, like a toolkit, designed from the ground up in C++ to be modular, supporting optimizations across the whole lifecycle: compile time, link time, runtime, even idle time. This makes a huge difference for performance. And that modularity, it's the complete opposite of those old rigid compilers. It gives you, the developer, much finer control over low-level stuff, things like data layout, memory management, JIT execution. Really crucial for high-performance code.
And it clearly worked because it's not just academic anymore. It's this big umbrella project now.
Yeah.
Used everywhere, Apple, Google, open source projects.
Oh, absolutely. You're almost certainly running code compiled with LLVM right now, probably without even knowing it. And the key practical idea for developers is this compiler as a library philosophy. Think of it like Legos for building compiler tools. Unlike, say, GC, where things can be very tangled internally, LLVM gives you these reusable library components, so you can build static analyzers, debuggers, specialized JITs, whatever, without reinventing the wheel every single time. That empowerment, having that fine-grained control over the low-level detail, that's a massive shift for developers building complex systems.
Okay, let's quickly tackle the name low-level virtual machine. We say it's not an acronym, but that virtual machine part, it still means something, right?
Yeah, it hints at the core concept. The intermediate representation, the IR, acts like an abstract machine's instruction set. It's virtual, in that sense machine independent, but it's low level because it's much closer to actual hardware instructions than, say, the Java virtual machine. It doesn't abstract away as much detail.
So it gives you more control.
Exactly. That lower level nature gives you more precise control. And that specific design point is why LLVM is so good at bridging high level languages and all sorts of different hardware. It can do powerful optimizations that don't depend on the specific target chip, but it still keeps enough detail to generate really efficient code for that specific chip. It's a very clever balance.
All right, let's talk about that core element then, the intermediate representation, the IR. You called it something between assembly and C. That sounds like the secret sauce.
It really is. Think of the IR as LLVM's universal translator. It's like a portable, high-level assembly language. And why that's so important is it decouples things. The front ends, the bits that understand C++ or Rust or Swift, they just need to worry about turning that language into LLVM IR.
Yeah.
And the back ends, the bits that generate machine code for Intel chips or ARM chips or whatever, they just need to worry about turning IR into that specific machine code.
So it simplifies everything. You don't need a completely new compiler for every language and every chip.
Precisely. It makes adding new languages or supporting new hardware vastly simpler. It's key to the whole ecosystem's flexibility.
And this IR, it's not just one thing, is it? You mentioned it exists in different forms.
That's right. There are three main ways you'll encounter it, and they're all interchangeable. First, there's the in-memory data structure the compiler actually works with internally. Then there's a human-readable text version, that's the LLVM assembly language, often in .l files. And yeah, you can actually read it, which is great for debugging or just understanding what the optimizer is doing.
Okay, that's pretty cool.
And finally, there's a compact binary version called LLVM bitcode, usually .bc files. Same information, just smaller and faster to process.
And this bitcode, it's used in the real world, right?
Oh, yeah. Big time. For a long while, from 2015 to 2022, bitcode was actually the default way you submitted iOS apps to Apple, and it's still required for watchOS and tvOS apps. Yeah, it shows it's not just theoretical. It's a practical way to distribute code, letting Apple, for instance, re-optimize apps for new hardware later on without developers needing to recompile.
Okay, now you mentioned something earlier. SSA, static single assignment. That sounds important for the IR. What's that about?
Right, SSA. It's a fundamental principle in LLVM IR. The core rule is simple. Every variable, or typed register, as LLVM calls it, is assigned a value exactly once. So if you think you're changing a variable's value in SSA form, you're actually creating a new version of that variable with the new value. The old one is still there, unchanged or frozen.
Assigned once and then frozen. Okay.
Yeah.
Why? What's the benefit of that? Seems kind of complicated.
It sounds it, but it actually makes life much simpler for the compiler's analysis and optimization passes. Because each variable version has only one definition point, tracking where values come from data flow analysis becomes way easier and clearer. It avoids complex analysis needed in non-SSA forms, like figuring out which possible assignment a variable use might refer to.
Okay. It makes the data flow really explicit.
Exactly. And when different paths of code execution merge, like after an if-else, SSA uses special instructions called PHI nodes. These PHI nodes explicitly select which version of a variable to use based on which path was taken to get there, maintaining that single assignment property. It's quite elegant, actually.
Got it. So for those maybe watching on YouTube, we could visualize this. What are the actual pieces you see in the IR, like the building blocks?
Sure. You got a type system, things like I1 for a single bit, basically a Boolean, I8 for an 8-bit integer, often a character, I32 for a standard integer, PDR for pointers.
The familiar types.
Yeah.
And instruction.
Yeah. The instructions often look like result, operation operand 1, operand 2. It's called 3 address code or 3AC. These instructions are grouped into basic blocks. Think of a basic block as a straight sequence of code with no jumps in or out except at the very beginning and the very end.
One entry, one exit.
Right. And each block ends with a terminator instruction, like braid to branch somewhere else or to return from a function.
And typical instructions would be things like add, load from memory, store to memory.
Yep. Call for functions, ICAMP for integer comparisons. And those FI nodes we just talked about. Seeing these actual instructions makes the IR feel less abstract, you know?
Yeah, definitely. You can see the structure, the low-level operations the compiler's working with before it gets to machine code.
Exactly. It shows you the sort of raw material that all those fancy optimizations operate on.
Okay, let's zoom out again. The whole compilation journey. You mentioned front ends, a middle end, and back ends. Can you walk us through that pipeline?
Sure. So it starts with the front ends. Their job is to take your source code, C++, Rust, Swift, whatever, and parse it, check it, and ultimately translate it into LLVM IR. The most famous one is probably Clang, which handles C, C++i, and Objective-C. It's known for being really fast and giving pretty helpful error messages, which is always nice.
I definitely appreciate it.
But there are front ends for tons of other languages too. Julia, Rust, Swift, many others. That IR acts as the common meeting point. Then that IR gets passed to the middle end. And this is where the real heavy lifting for optimization happens. It takes the initial IR and applies potentially dozens of analysis and transformation passes to make it better, faster, smaller, more efficient. There's even a tool op that lets you experiment with these passes directly on the IR yourself.
And you mentioned some advanced strategies here, like link time optimization, LTO.
Right, LTO is cool. Normally, a compiler optimizes one file at a time. LTO delays some optimization until link time, when the compiler can see all the code from different files together. This allows for more powerful whole program optimizations, like inlining functions across file boundaries, stuff like that.
That makes sense, having the bigger picture.
And then there's profile-guided optimization, PGO. This is really clever. It's usually a two-step process. First, you compile your code with instrumentation added. Then you run it with typical inputs, and the instrumentation gathers data like which parts of the code run most often, which branches are usually taken.
So real-world usage data.
Exactly. Then you recompile, feeding that profile data back to the compiler. The compiler uses that info to make smarter decisions, maybe aggressively optimizing hot paths or arranging code better. It makes compilation more dynamic, guided by actual behavior.
And all these optimizations are done using passes, right? You mentioned analysis and transform passes.
Yeah, LLVM has this modular pass system. Analysis passes just gather information like DOM tree figuring out the control flow structure. Transform passes actually change the code. Things like LLVM, loop invariant code motion, which pulls calculations out of loops if they don't need to be repeated.
Oh, that's a classic one.
Yeah. Or mem2reg, which tries to keep variables in fast CPU registers instead of slower memory. Or GVN, global value numbering, which spots redundant calculations. Loop unroll is another common one. There are tons of these passes working together.
Okay, so after all that middle-end optimization, the IR is looking pretty good. What happens next? The back end.
Right, the backend. Its job is to take that highly optimized LLVM IR and turn it into actual machine code for your specific target architecture, Intel by 86, ARM, RISC-V, whatever. The LLC tool is the command line interface for this part. This is where the code gets ready to actually run on silicon.
And that involves more steps.
Oh, yes. Several crucial ones. First is instruction selection. This is mapping the abstract LLVM IR instructions to the specific machine instructions available on the target CPU. It's a complex matching game, often using frameworks like selection DAG. Then there's register allocation. CPUs have a very limited number of super fast storage spots called registers. This pass figures out how to best use those registers for the variables in your code.
It sounds tricky. What if you run out of registers?
That's called spilling. The allocator has to store some variables back into main memory, which is slower. So good register allocation is critical for performance. Algorithms like graph coloring or linear scan are used here, balancing optimality versus compile time.
Makes sense. What else?
Instruction scheduling. Modern CPUs can execute multiple instructions at once using pipelines. Scheduling reorders the machine instructions to keep that pipeline full and avoid stalls, maximizing parallelism.
Getting every last drop of performance out of the chip.
Pretty much. And finally, all this leads to assembly generation, creating the human-readable assembly code, often with debug info. Then that gets assembled into binary object files, linked together, and you get your final executable program precisely tailored for the target platform.
Wow. That's quite a journey, from source code all the way down. So just to kind of wrap up the big picture, LLVM's power comes from that modular design, the universal IR acting as this common language, and then this really sophisticated pipeline with all those optimization passes.
That's a great summary. And connecting it back to you, the listener, this whole infrastructure, it's really changed how software gets built. It lets developers like you build faster, more efficient systems, and it drives innovation because it's so adaptable to new languages, new hardware. It's a really powerful enabler.
So here's a final thought to leave you with. Given how flexible and extensible LLVM is, where do you think it goes next? What new frontiers might it open up as hardware keeps changing, as new programming ideas emerge? How could understanding LLVM help you build the next cool thing, maybe even your own language or tools? Definitely something to think about.